right, let's get started, everybody. We are happy to have Robert Pincus joining us today from Lamont, Doherty Observatory and Columbia University. Robert got his PhD in 1994 from the University of Washington. He did a postdoc at NASA and then spent some time early in his career here. And then in Boulder, Colorado with Series for a long time, but then for the last few years now at UW-AOS in Columbia. You've maybe seen him or his name around in various places over the years. He's had various leadership positions, like the editor of Journal of Advances in Modeling Earth Systems for 5 years, and now on, is it called the Committee for the Climate Model Comparison Project?
The panel.
The panel, the CMIP panel. So, all right. Take it away, Robert.
So could you cut the light? It's the one next to the door. Yeah. And then, yeah, if you want to unmute.
I was going to not use this thing, but I feel like maybe I should use it so I don't have to shout. It's a pleasure to be back. I taught radiation in this classroom in the 90s. The classroom's been upgraded. People have been upgraded. I'm not Galen McKinley, who was here 2 weeks ago, although I am teaching a course with her at Lamont. Okay, so that's all. I'm going to talk about 2 ways today, so you'll have to bear with me because I really was putting these slides together on a plane, partly because the work is very new, and it's very exciting. Hopefully I will make it coherent. The theme that ties these 2 ideas together is radiation sculpting the behavior of the atmosphere. One of them is a fairly large-scale thing. This is the hydrologic sensitivity, or why there's more rain when the atmosphere gets warmer. And the other is fairly small scale. It's related to the organization of clouds in the trade wind regions. I'm going to do a bunch of calculation, none of it, although I've spent a lot of my career building complicated radiation models. I'm not going to use any of them here. I'm going to do a whole bunch of idealized calculations. Some of that is a shift that I made kind of deliberately when I moved from a place that's focused on prediction to a place that's focused on understanding. So I wanted to build less and learn more. That was sort of a very explicit goal for me. I was a physics major, and one of the things that's attractive to someone like me about radiation is that it's tied to classical physics from the 19th century. So radiation was recognized as an electromagnetic wave in 1872. And it ties to 20th century physics. Partly the particle scattering was developed during that time. Partly quantum mechanics helps explain spectroscopy. That is to say, the absorption, the way that gases interact with light, and why the absorption changes so rapidly with wavelength. So it has this deep tie to theory. We don't really tend to use theory when we explore ideas about how radiation couples to the rest of the climate system. We've mostly done that through computation. And so what that means, because we're doing it through computation, it means that we wind up sort of interpreting results or idealizing problems. I'm going to turn the clouds on, I'm going to turn the clouds off, right? But it's very hard to get kind of a first principles understanding. There has been a resurgence in the last 5 years, I would say, really starting in 2018, for idealized theoretical modeling of precisely that coupling. This has the spirit of the kinds of work that like Angel Adames-Carliza or Larissa Back do in the field of dynamics that's now being kind of extended to radiation coupling to the climate system. There's a few things that have been learned. These are some of the highlights that have been learned in the past couple of years. Why is outgoing long-wave radiation at the top of the atmosphere roughly linear in surface temperature? If that OLR depends on sigma t to the 4th, you'd expect that to be cubic. Why do the tropics cool at roughly 2 Kelvin per day through the entire depth of the tropics? Try explaining that with a gray radiation model. It would be impossible for you. These 2 are going to feature in the talk. The pieces of physics behind this are going to feature in the talk. Why is forcing by carbon dioxide, radiative forcing by carbon dioxide, logarithmic in concentration? Why does it depend on the state of the atmosphere? These are all really interesting questions. Many of them have been addressed by these 2 young folks down here. So Nader Jivanji, it works now for NOAA at GFDL. And Daniel Kohl is a German guy raised in East Africa who is now working at the University of Beijing. There are three important facets that I will use. Many of them are sort of inherent to this, to these developments. One of them is looking at things in a spectrally resolved point of view. So this axis is wave number. You'll be seeing it quite a lot. It's the inverse of wavelength. That has value because it turns out that particularly the clear sky, and I should maybe stress here that all of the problems I'm talking about are going to be clear sky and long wave. So it's emission and absorption and only in clear skies. That behavior is dominated by a relatively small number of components of the atmosphere. Water vapor absorbs in the far infrared. These are very long wavelengths. And it absorbs in the mid-infrared. In the middle of that absorption band, there's a window, right, where you can see the surface. This is the basis for our ability, for example, to sense the surface, to see the temperature of the ground from outer space. Inside this window, there's absorption, a little bit of absorption by ozone, and a little bit of absorption by carbon dioxide. This plot that I'm showing you is the spectrally resolved climate feedback parameter, as inferred from observations by Florian Römer, who's a graduate student at the University of Hamburg. So the one probably to look at that's most relevant for long-term change is the blue, which is the which is derived from interannual variability, by looking at how temperature and OLR co-vary on interannual timescales. And what you'll see is that the dominant atmospheric feedback comes from the water vapor window. So most of that is, of course, coming from changes in the surface. And that much of the rest of the atmosphere has either no response to CO2, no response to surface temperature, or a relatively modest response. So this water vapor window, just to orient you, is from about 8 to 12 microns, if that's your sort of view. So the spectral view is one facet. There's two important idealizations. One of them is that, for those of you who've taken the radiation course know, it's the quantum behavior. It's all these quantum transitions that determine the absorption spectra of gases. The absorption spectra for CO2 is super complicated. The absorption spectra for water vapor is even more complicated. And that fully resolved, spectrally resolved calculations are in this big gray cloud here. This is orders of magnitude in opacity across relatively fine spectral intervals. And the insight that Cole and Givenchy and others had is that you can really just draw straight lines through a bunch of this stuff. If what you're interested in is the spectral integral, you can ignore a lot of this detail and draw straight lines. And then for carbon dioxide and for water, these straight lines don't depend very strongly on temperature. They don't depend very strongly on pressure. And this allows you to do sort of very simplified calculations. One wrinkle with respect to water vapor is that the water vapor window is not fully transparent. There's weak absorption from something called the continuum, which I'll talk about a little bit later, which puts kind of a floor on absorption. And that floor rises as, so that is to say the atmosphere becomes more opaque, even per unit water vapor, as temperature increases. We idealize the spectroscopy. We can also idealize the radiative transfer. These plots are the same. One is with respect to optical depth, and the other is with respect to pressure. And the thing that I'm drawing out here is just the idea that cooling in the atmosphere is dominated by the extent to which any given layer is cooling to space, is able to emit to space. And for reasons we'll go through later, what this does is it introduces a peak in cooling. So I can point you to the paper here, and it's a terrific piece of understanding. But what I want you to see is that this blue line says cooling to space, that these are from radiative convective equilibrium simulations with different kinds of thermal stratification. What you see is that if you think about it in optical depth units, that the cooling is, of course, near the low optical depths. But if you think about it in pressure units, so that is to say how much are you warming or cooling per increment of pressure, you see that the radiative cooling is dominated at about optical depth 1. And that's true for either of these kinds of stratifications. So we'll use this idealization over and over again, this cooling to space idealization, throughout this talk. So let's talk about the small scale, about the organization of clouds in the tropics. This is Benjamin Fildier. He's a postdoc in Paris. And he's working with Carolyn Miller and I and Stefan Voigtlichsteiner on this paper, which will come out in AGU Advances any day now. And this is the title, How Moisture Shapes Low-Level Radiative Cooling in Subsurface Regions. This question arose during a field experiment called Eureka, which was mid-January to mid-February of 2020. So we really just inched it out before the pandemic started. Held in Barbados, off the island of Barbados in the Caribbean. And so this is a region of trade wind clouds, so there's dry subsiding air. We were interested in, there were, I don't know, 30 or 40 different platforms, some of them automated, some of them airplanes, surface ships, and so on. But we were interested in characterizing the relationship between clouds and the large-scale environment. So there were many ways in which we measured clouds. The large-scale environment we measured with thermometers hanging from balloons, which is to say radiosondes and dropsondes. So the radiosondes were sent up from Barbados, the island itself. We had ships in our study area here off the island of Barbados. And we had 2 high-flying aircraft, one of them the German G5, the hollow aircraft flying at about 9 kilometers. The other, the NOAA Hurricane Hunter P3, which could fly at about 7 kilometers. And these deployed between them about 2,500 sondes over the course of a month. So the white ones are from the dropsondes. The dropsondes have a little parachute, but they more or less drop like a rock. So about 1 meter per second, and so they don't travel very far. The balloons, of course, go up into the stratosphere, and they take about an hour and a half to do that, and so they travel. So 2,500 sondes, 1,500 of them launched from the surface, about 1,000 thrown out the back of the plane. I dreamt the sound of deploying dropsonde for a month after the experiment. Okay, so there's these 2,500 sounding profiles made in this relatively small region, right? This is only about 10 degrees of latitude and 10 of longitude over the course of the experiment. Yes, this is a circle. The German G5 flew in a circle over and over and over again for reasons I could explain later. And then what we did, Annalea Albright, who was doing her PhD in Paris at the time, then took these profiles and computed radiative heating from sunlight and radiative cooling from long-wave radiation. And of course, she computed that. And the first thing that we noticed, and this is just a time mystery, right? So this is starting at the beginning and going to the end, and every single radiative cooling rate is on here. And the first thing you notice is that there's not a lot of cooling in the free troposphere. And there's really a kind of a sharp peak at about 2 kilometers. Most of the time. Sometimes you get these sort of filaments which seem to start up high and come down low. Okay? But really, the cooling is not uniform, like we're used to thinking of it in the tropics. But rather, there's this fairly sharp peak, and this is kind of 3 or 4 Kelvin per day against a background of about 1 Kelvin per day. And the question is, why? Why do we have that structure of cooling? So the trade winds are in the descending branch of the Hadley cell. Yes? Sorry, I'll treat it like a class. If you're on, is there a question or no? You good? Okay. Totally. You can wave your hand off. Yeah. Okay. So the trade winds are in the descending branch of the Hadley cell, and what that means is that the air is dry and it's warm, but underneath that is this moist boundary layer, right? So the radiative cooling, as it turns out, is associated with this jump in relative humidity. So here the colors sort the two into whether the peak in radiative cooling is down low or up above. Yeah, let me see if I get that right. And you see here the radiative cooling, is dry all the way down to about 2 kilometers and then goes up. And for this is all, I should say, all these soundings are drawn from one day, from sondes deployed on one day. Whereas the soundings which have a higher peak also have a higher peak of cooling. The lower peak of cooling is associated with this kind of almost a step function in relative humidity at about 2 kilometers. The higher peak of cooling is associated with these excursions up high. So it seems like the radiative cooling is associated with a strong gradient in relative humidity. You can't really, I just want to point out, you can't really observe these things from passive sensors because the vertical resolution is much larger than this vertical extent of this jump. Right? So those will get blurred out in any kind of remote sensing, of passive remote sensing. Why might that be important? Why might it be interesting that we would have radiative cooling up high in some parts of our domain and radiative cooling down low in others? Well, if you look at simulations of self-aggregated deep convection, like down here. So often we'll do a problem in which we have radiative convective equilibrium, so there's no external forcing, there's just radiative cooling, which is balanced by emergent convection. And if we do that in large enough domains, we find that rather than staying like popcorn cumulus with homogeneously distributed convection, all that convection tends to concentrate into a small area surrounded by large expanses of dry air. If you sort such a domain in terms of increasing precipitable water, so integrated water path, you see low-level cooling down here in the very driest parts of that simulation, increasing with height. You can compute the stream function, and it suggests a circulation which is driving moist static energy up gradient into the convective region. So this is how the convection self-aggregates. These low-level circulations driven by, in deep convection, driven by this horizontal gradient in the height of this peak cooling can drive the moist static energy up gradient. And if we go to observations from a single day during Eureka, we see something like the same thing. This is it is the same vertical axis. Sorry, I took it back. So in the dry regions out here away from the clouds, we see low-level cooling. In the moister regions where the clouds are transporting vapor up high, we see cooling up high. So the suggestion would be that there could be circulations which are driving the moisture towards aggregation and helping these clouds to organize. So that's why we care about where these vertical peaks of cooling come from. So how do those gradients in relative humidity lead to strong cooling? Well, the first thing we'll do is we'll invoke cooling to spaces. I'm going to walk through some algebra or some math, but the physics behind it is all very straightforward. So our spectrally resolved heating rate, the heating rate is a function of the wave number nu, is a scaled version of just the divergence in flux coordinates. How much more energy is leaving some unit pressure level than is coming in. And by invoking cooling to space, what we can say is you have a local black body emission, you have a local Planck function. And so this heating rate is driven by how much the transmissivity, the opacity, changes across that layer. Transmission is e to the minus tau, and so what that means is that change in transmissivity is the transmissivity itself times the change in optical depth with unit pressure. Okay? We're going to define a lapse rate of optical depth, a logarithmic lapse rate of optical depth. We're going to call it beta, so this is the change in the logarithm of the optical depth with respect to the logarithm of pressure. We do that because, for example, for a well-mixed gas, this beta is 1, right? So if there's no variation in height, then, you know, basically the opacity increases as the mass increases in a logarithmic sense. Right? For a gas like water vapor, that increase is more rapid because there's a correlation between pressure and temperature. And water vapor concentration with temperature through Clapeyron. So that means that the heating rate looks like beta divided by the pressure times this term, which is what we think of as a weighting function. For constant beta, this is the cooling to space term that maximizes at tau equals 1. Now we will idealize the spectroscopy in the same way that I showed you before, which is to say we're going to talk about the peak absorption at one part of the spectrum, and then we're going to let the absorption coefficient decay exponentially away from that peak absorption. So if you draw this as the log of absorption versus wave number, that'll be just a straight line. That's the other ingredient here. Idealized radiative transfer, restricted to cooling to space. All the cooling is cooling to space. Idealized spectroscopy, we're going to draw those straight lines through the wave number absorption coefficient. And this is actually the basis for this paper by Givenchy and Feuglestaller in 2020. So here are already coarse-grained line-by-line calculations. This shows the absorption coefficient as a function of wave number. This shows the log of the of the optical depth, or the scaled optical depth. And the main thing you want to see here is that this line this jaggedy line corresponds to where tau equals 1. And what you see over here is the cooling rate as a function of the wave number. Okay, so he's got a single idealized profile here, in which he's not computing. Here's the absorption coefficient, here's the optical depth as a function of wave number here, and here's the cooling rate. And what you see is that the cooling follows this tau equals 1 line. So cooling to space is a pretty good approximation. What's happening over here is just that there is cooling, but it's very hard to see because the atmospheric Planck function is much smaller at these wave numbers than it is at these wave numbers. Okay? Here is the model I was just describing for you, idealized in the same way. Here's the straight line, right? Here is the optical depth and the iso lines of tau equals 1, and here's the radiative cooling. So this is partly meant to be, it's meant to be two things. One is a motivation for how cooling the space works. The other is an explanation for why cooling is more or less constant with height. And so what happens is, if we say that all the cooling happens at tau equals 1, what that means is that there's some range of wave numbers at any given height that are more or less reaching tau equals 1. Right? What range of wave numbers that is depends on how much water vapor is above you. Right? But the reason that you can keep cooling all the way to the ground is because you have this wide range of opacities of water vapor. So this physics is going to turn out to underlie essentially everything else that I showed you. We're going to do one further simplification. We're going to just say that there's what you would say, no pressure broadening. There's no other dependence of the absorption coefficient except on the wave number. And so what that means is that we can change this beta to something which is the logarithmic change in the water path with height, with pressure. Okay, and so then there's some scaling factor out here to account for the absorption coefficient. And then there's just this definition that says that the total cooling is going to be the spectral integral that has these three terms in it. There's the black body emission, there's that vertical weighting function, and there's this beta where now I'm saying that lapse rate can vary with height. Planck function, vertical weighting function, height-dependent water vapor lapse rate. Maybe I would just point out to you here that if you have constant relative humidity, this beta is also constant. So let's examine all of these terms in real soundings. This is, again, just a single day of Eureka. The lines are coded according to the precipitable water. And so here is the relative humidity. Ignore the black for just a second. Here is the relative humidity in all of these soundings. Here is the saturated specific humidity. But maybe most importantly, here's the water vapor path. This is the logarithm of water vapor path. So this is sort of half of our beta. If you squint, you can see there's obviously a big change in the slope right here, which is going to correspond to our radiative cooling. So now what we can do is radiative transfer calculations that include each one of these terms independently. This one is the change in the Planck function that results as this is the Planck function as a function of height. And you can see that, yeah, there is some small excursion, but that is clearly not what is driving. The slight warming at that inversion is not what's driving our peaks, our cooling peaks. The vertical weighting function here has kind of the right sense in that it's located at about the right height, but the peaks are very broad. And so I should maybe say that this is actually, these are the cooling peaks, or this is the cooling rate as a function of pressure that we're seeing in each one of these soundings. It turns out that the thing that tells you most about not only this spiky peak, well, maybe I'll just say, the thing that tells you most about the peaks is indeed the lapse rate of water vapor path with height. So it really turns out that these jumps in relative humidity are the thing that tells you where the peaks ought to be. So why is that? Well, the sharp gradients increase the rate at which that packet of wave numbers reaches tau equals 1, right? So you're going along and you're accumulating packets of tau equals 1 as you go down, and all of a sudden you've got a whole bunch more water vapor and a whole bunch of wave numbers are able to cool to space effectively, right? As you descend away from that step into the atmosphere becomes opaque again, or maybe the way to say it is that the relative humidity looks uniform because the radiation's happening from, at any given wave numbers, happening from a relatively narrow height. Some things to which I would refer you, which are in the paper. One is that you saw these filaments of cooling coming down. Those corresponded to moist intrusion, so water, relatively high concentrations of water vapor, relatively high in the atmosphere, which essentially used up some amount of those wave numbers. So that's sort of interesting. The idealization that we used here, this black thing, is when we introduce a step function in relative humidity. And what that will tell you, and then a power law in approximation to Clausius-Clapeyron, let's say. And that tells you two things. One of them is that the peak cooling scales as the ratio of the relative humidities in the free troposphere and the boundary layer. And the other is that it explains the shape that we see here, a very sharp cooling near the hydrolapse, near the humidity inversion, decaying back towards this value as you descend. Yeah.
Rob, are those moist intrusions that you are speculating are part of the answer there, are they forced from remote convection or
Yes.
local?
Oh, I don't know that forced from convection at all.
Oh, okay. But do they invade from remote
They
locations?
invade from remote.
That's what I guess I should have asked. Okay.
Yeah, because the convection's not, well, I thought it was never deep enough to give you something at 6 kilometers, except we did some overnight flights.
Yeah.
And then we saw in the middle of the night, under the full moon, like convection going to 8 kilometers after seeing it all being restricted to 4 for a month. So,
Interesting.
yeah. And maybe this is the link. If you look here at the mean relative humidity in the free troposphere, against here the cloud fraction. And here this is really just meant to tease you a little bit. During Eureka, we were thinking about the organization of clouds in terms of these four kind of flavors, these fish and flour and gravel and sugar. These two tend to be deeper, this one tends to be intermediate, and this one tends to be shallow. And what you see is that there is this association between a drier, free troposphere and more cloudiness, and particularly more aggregated forms of convection. So I'm trying to tease you a little bit with this understanding of where the humidity peaks come from. But if you'd like to understand the link to the cloud organization, I would just refer you to that paper. Okay. So the second question that I want to address is why it rains more when the planet warms up. And this grew, I taught radiation to the bunch of applied mathematicians last fall. This started as Sean Cohen's class project. Sean does not have any pictures on the web, so he gets XKCD. And this is like super, it's not even half-baked. Like, we're working on this, and I was making plots yesterday. So the first question would be, why does radiation have to do with precipitation? And of course, this is a figure from a paper that Tristan did. It comes because both the energy budgets and the water budgets in the atmosphere have to balance. And the energy budget of the atmosphere includes a component that comes from latent heating. So that is to say, the energy that's received at the surface evaporates water, which goes into the atmosphere. Some of that water condenses and falls out as rain, leaving that energy behind. That residual energy has to be removed by precipitation. And so the evaporation and the precipitation have to balance each other on the global scale, in a closed system. So in our case, on the global scale. So this is why these things are linked. How will they change? Well, this is the picture in the present day climate, and we think of this as being hydrologic sensitivity. So it's sort of the hydrologic analog to climate sensitivity. And the way that we typically express this is as the rate of change of precipitation per unit warming of the surface. So how much more rain will there be as the surface temperature increases? And that how much more rain will there be is associated with how much more net atmospheric cooling will there be. And that association is stronger than this link, than the link between mean cooling and mean precipitation, because the other terms in the energy budget are expected to change much less than the evaporation term of the surface. This has been understood for quite a while, and this Heldon-Soden paper from 2006 says, well, the sensitivity is on the order of 2 degrees Kelvin per, 2% precipitation per degree Kelvin. Looking at CMIP5 models, median value about 1.7. The main point here is that it's much weaker than Clausius-Clapeyron scaling, which is about 7% per Kelvin. And so the question is, why 2%? I mean, 7% would be a reasonable upper bound, right? Why 2? Why not 1? Why not 6? Why not a 10th? Why? I have to take you on a little detour here. In order to understand that 2% per Kelvin, I have to take you on a little bit of a detour. And this is through one of the aspects of physics that I mentioned at the beginning, one of the explanations that had arisen in the past few years. If we look at the radiation emitted to space, as it depends on the surface temperature, we see that the OLR, the outgoing long-wave radiation, is linear over a pretty wide range, kind of 40 Kelvin, 45 Kelvin of surface temperature. Even though sigma t to the, if you take the derivative of sigma t to the fourth, you of course get something which is cubic. How does that linearity arise? Well, it arises, part of the explanation is here in this paper from Daniel Cole and Tim Kerr. Thermal emission to space decouples from the surface temperature in optically thick regions of the spectrum. So the way this linearity turns out to work, and I'll show a figure so you don't have to keep this all in your mind, but is that as you increase the surface temperature, you want to emit a lot more. But the optically thick parts of the spectrum are also increasing. As you add more water vapor, you make the atmosphere more thick. The part of it that goes from optically thin to optically thick is the edge of the water vapor window. So the water vapor window starts to close. And that closing of the water vapor window happens at a rate that more or less exactly compensates a bunch of the increase in surface emission. So the surface emission is in fact increasing, but the water vapor window is closing. And you can see that in a figure from their paper. So down here, you see the transmission. They're doing a single idealized atmospheric profile across 80 K of surface temperature, 240 to 320. This is partly because Daniel Cole is actually kind of a planetary guy. And so you see here the emission, and you see here the transmissivity of the atmosphere. And what you see is that at very low temperatures and hence very low water vapor amounts, you have a big wide water vapor window, where window means you're fully transmission of one across a wide range of temperatures. And as the surface temperature increases and the water vapor burden goes up, you see that that you get this transmission one over a narrowing range of surface temperatures, until by the time you're down here, there isn't any part of the atmosphere that's fully transparent. And that would be a runaway greenhouse. So why is this emission decoupled from the surface temperature? Well, it turns out to be specific to water, which on our planet condenses, right? And the equation, the relationship that governs that is the Clausius-Clapeyron equation, right? But this wouldn't work on moons with methane oceans too. The same physics works, right? Because water vapor is condensing, because the maximum amount is controlled by Clausius-Clapeyron, it means that water vapor for a given relative humidity, the water vapor path at any height of the atmosphere is purely a function of temperature. Right? If you fix the relative humidity, then water vapor path is purely a function of temperature. And that means that the height at which you reach this cooling, right, or the height at which the atmosphere becomes opaque, is purely a function of temperature. And that means that the height at which you are doing the cooling is always at the same temperature. So it's completely decoupled from the surface temperature in the limit of something which is optically thin. This was first noticed in 1928 by George Simpson. It was dropped until about 2010 when William Ingram noticed it again and mentioned it. And then Givenchy and Cole have both brought this up. And so now it's kind of got this name of Simpson's law, and it's just here in words. The first order, and assuming that relative humidity doesn't change, the OLR at regions which are dominated by water vapor doesn't change with surface temperature. So how is that related to hydrologic sensitivity? Well, what we're going to do is we're going to think about hydrologic sensitivity as a function of the temperature. As a function of the wave number. So we are going to assume here that column integrated, so I'm not now thinking of the cooling at a given height, but I'm just asking what's the net cooling of the entire column at any given wave number. This is dominated by cooling to space. So here is my black body term. Here's the temperature at a given height. Here is the transmission to space. So at any height, this should be a tau prime nu, right? At any height, we have emission, which is attenuated to space. And we're going to integrate across all those heights from the bottom to the top, or actually from the top of the atmosphere to the bottom to get the net cooling. I can change variables to express this as an integral over transmission. And then I can differentiate this change, or this integral, with respect to surface temperature. So this is going to tell me how does the net integrated cooling change with surface temperature. We'll do a little bit of calculus, some Leibniz rule. The upper limit doesn't change, but the lower limit does change. We have this, and then we can bring this derivative inside. So we have the change in the emission temperature at a given transmissivity with respect to surface temperature. This is precisely the thing that's zero under Simpson's law, right? Because this says how does the blackbody emission change as a function of transmissivity? But the transmissivity is just completely controlled by temperature, so there is no derivative here. Right? So this entire integral drops out. We're going to assume that that the surface air temperature is the same as the surface temperature. Close enough for rock and roll, and then we're just going to use some identity here to get at this. So we have the spectrally resolved cooling is this. It is at any given height, at any given wave number, it's the black body emission at the surface temperature times the transmissivity times the rate at which the atmosphere is getting a little bit thicker in optical depth units. And because we have assumed, we're ready to assume that there's no, that the only thing this depends on is water vapor path, then we can write it as this absorption coefficient times the rate of change of water vapor path with surface temperature or Clausius Clapeyron. So what does this mean? Well, first we're going to use this distribution of water vapor absorption, right? Again, this kind of linear fit so this is the log of the absorption coefficient as a function of wave number. Here is the water vapor window. Why are there two large excursions? Right? These correspond to rotational transitions, and these correspond to combined vibrational and rotational transitions. Okay? So that's why there's these two broad bands of water vapor absorption. We're going to use that. And then we're going to do an idealized profile. It's basically a moist adiabat to a fixed tropopause temperature. The only thing which is in our atmosphere here is water vapor. And then we're going to plot the sensitivity as a function of the wave. Okay? And so what you see is that the sensitivity is small at the edges, because that's where Simpson's law is holding true. Right? So where the atmosphere is optically thick due to water vapor, there is no sensitivity. At wave numbers at which the atmosphere is optically thick due to water vapor, there is no sensitivity. And the sensitivity comes at the edge of the water vapor window, but the size of the water vapor window depends on surface temperature because it depends on the water vapor path. So as you get closer and closer, as you raise the temperature and raise the water vapor path, the water vapor window narrows, and the sensitivity goes up a little tiny bit. Here's the water vapor window, and so the sensitivity goes up a little tiny bit with surface temperature. The water vapor window is not transmission. Here's the physics behind that. The hydrologic sensitivity is also the result of the linearity of OLR with surface temperature is precisely a result of the closing water vapor window. So the optically thick spectral regions get bigger and the window gets smaller. The water vapor path increases roughly exponentially with surface temperature, and that coincides with this, where that compensates for the roughly exponential decay of absorption coefficient. As I said, the water vapor window is not transparent. It's a little bit dirty. And that dirt, so to speak, that spectral dirt is what we call the water vapor continuum. And that's a couple different things. It's partly water vapor is polar, so there are dimers in the atmosphere. These two loosely bound multi-molecular complexes. Also, you are very far from absorption lines, but there's a whole lot of water vapor absorption lines. And So the continuum may be part of that. But the result is that we know empirically that there's a low level of absorption in the water vapor window. And now we want to include that here by just adding a constant lower bound. Because this changes the picture actually pretty much. So now we still have a narrowing water vapor window, but there's a finite hydrologic sensitivity that comes because as you increase the temperature, this little bit of absorption starts to muddy your view, right? And so you get some finite sensitivity, and actually that sensitivity gets fairly large until at the very highest surface temperatures, it gets smaller. And that's because what's happened between 290 and 300 is that the water vapor window has closed entirely, right? The continuum is now starting to make the water vapor window itself entirely opaque. And what's going on here? And so that has these implications for the sensitivity. That it gets substantially larger, that this rate of increase with temperature gets substantially larger until the water vapor window gets opaque somewhere out here and falls off. You can take the same very idealized atmosphere and run it through a line-by-line model. So here the main difference is both that the radiative transfer is not approximate anymore, and the water vapor spectroscopy is not approximate anymore. It's still an atmosphere in which there's only water vapor, so there's a lot missing. And you can see that the spectral agreement is okay. It's not terrific. You do see these, these peaks, but there are a lot more muted. But it turns out that the spectral integral is fairly forgiving. So that is to say, the blue here now is the line-by-line model in these idealized atmospheres. The black is our analytic model, integrated numerically, I want to say. And you see that they're not so different. So this water vapor window, the dirty window, the water vapor continuum, amplifies the hydrologic sensitivity. Yeah, basically just because the opacity increases with temperature by a little bit at very low temperatures and by more and more at higher temperatures until you get to a runaway greenhouse. Maybe you noticed, probably you didn't, that I changed this from how much will it rain more as surface temperature increases to why and how. And that's because we're missing a couple of pieces of physics that we are in the middle of trying to add. One of them is the effect of other gases, so carbon dioxide, ozone. They're both going to mask some of that sensitivity. If you went back and tried to translate these values into percent per Kelvin, you're up at about 8% or 7% per Kelvin here. So these are big overestimates. So some of it is that some of what's missing there is masking by carbon dioxide, by ozone, by clouds, which I haven't put there. One of them is that there is actually pressure broadening. So that is to say, there's a pure dependence of pressure, of absorption coefficient on pressure, which we have not bothered to deal with, but expect to do. And the one that is most interesting to me is that the actual the net cooling of the atmosphere also includes exchanges with the surface. And we think, but we haven't worked through all the details, that there's some interesting things that happen because as you, roughly speaking, the rate of change of downwelling long wave is different than the rate of change of upwelling long wave into the atmosphere. So stay tuned. We're going to keep working on this. I didn't really have a conclusion. I wrote this. I'm interested in this sculpting, how radiation, controls, or the extent to which radiation controls atmospheric phenomena. I've used these three ideas. Two of them are sort of simplifications that we think we can get away with. One is cooling to space. The other is Simpson's law. Useful as a thinking tool, doesn't really hold, but useful as a thinking tool. And this idealized spectroscopy. And I've applied them to these two really different contexts. One of them is the organization of small clouds as it's driven by the low-level radiative cooling peaks, which turn out to be related to gradients in relative humidity. And the other is hydrologic sensitivity, which is governed by, both of these are governed by kind of this link between the thermodynamic and the, and the spectroscopic behavior of water. I'll stop there. Thank you very much for bearing with me.
Thanks a lot, Robert. Any questions?
Yeah, forgive me if this is a simple question because I'm not super well versed in this, but you're talking about the sensitivity to changes in the temperature warming lower once you reach above that certain threshold because the water vapor window is closing. So that temperature is lower than what you would expect surface temperatures to be in the tropics right now.
Yeah.
So would it be correct to say that in a way, like, the tropics are already under runaway greenhouse, and the fact that the whole planet isn't is because there's an ability at the poles of the planet to get rid of extra energy that stops the runaway from taking over the whole planet?
Super good question. Are there radiator fins? The answer is yes. It's a little bit more complicated. So, we saturated the atmosphere through its depth. It's very, very simple. There's no cloud masking. So we're probably being a little overly ambitious. But yes, it is true that surface temperatures in the tropics, if the whole planet were that temperature, would lead to runaway greenhouses. It is not just the poles, but the subtropics, which do subtropics not only because they're colder, but also because they're drier, which lead to planetary stability. So the answer to your question is partly yes, and partly, well, we were sloppy, and maybe that's overstating the case.
And so as you warm, you're basically moving that threshold farther and farther into the subtropics, where because as you warm, you're closing that window off in a bigger and bigger portion of the planet.
Yes, I think that's a fair interpretation. If you were going to, so each one of these calculations is done with a single profile, a highly idealized profile at a single surface temperature. If you wanted to get an estimate of the global hydrologic sensitivity, the least thing you would have to do would be to convolve that with like the probability distribution of surface temperatures. So that interpretation sounds right to me, that you would be changing, under planetary warming, you would be changing that distribution of surface temperatures.
Thank you.
Do you have a question?
I'm just leaving the students to have ask
Okay.
So, yeah, I see a couple of students asking questions, so I'll go when the students are done.
Okay, cool. Julia?
Yeah, great talk, thank you. So I'm curious, so going back to the work on the radiative cooling component and the self-aggregation versus with luminosity observations, I'm aware that the processes for self-aggregation to occur are, very much dependent on the model and the initial conditions, boundary conditions and such. But I just was wondering if you could expand a little bit more on the radiative cooling component in the self-aggregation model and comparing that to the observations. Is there essentially a similarity in the processes? I was following your argument a little bit, but
The first thing to say is that this is meant to be like bait,
Yeah.
This is meant to try and encourage you. So Carolyn Miller and Ben Fildier are interested fundamentally in this convective organization.
mm-hmm.
I got them interested in this question of the low-level cooling rates because it was the first thing that popped out at me. And I'd been interested in this ever since I read the Feugler-Staller and Givenchy paper earlier, or Givenchy and Feugler-Staller paper earlier. So the argument goes like this. So just to be clear, what happens if you take an unforced simulation of convection and you just let the radiation destabilize the atmosphere, and you let the convection restabilize the atmosphere. You get this state called radiative convective equilibrium. This is the problem for which Suki Manabe won the Nobel Prize in 2021. It's a problem that can be applied to all kinds of different models, and if you do it in a model that resolves the motions of the clouds, the convection, if you leave it for a very long time, the convection will tend to clump. So that's the self-aggregation of convection. People looked at that and they thought, what the hey? Like, why is that possibly true? The surface is completely uniform. There's no interaction with the surface. The surface is completely uniform. So how does it go from homogeneous convection everywhere, popcorn convection, to this big clump? So that's what motivated analyses like this, which comes from a paper of Joe and Mithers. And essentially all that you do is you sort their domain into columns of precipitable water. You compute the radiative cooling in each bin of precipitable water. And then you ask for this profile of radiative cooling, what is the implied circulation? And that implied circulation is up gradient. The flow should be from the dry columns to the moist columns. So that suggests that in that circumstance, the convection is being aggregated because the profile of this cooling promotes the flow from dry regions into moist regions. Low-level flow from dry regions into moist regions. That's what happens in these idealized simulations of deep convection. There is a similar gradient in height from low to high, from dry to moist in the shallow convection. That basically corresponds from low to high in this picture. And we hope you believe that these two things are related.
Time for another question.
With all those soundings, maybe the link is PV. Because if you've got cooling that slants in the vertical, there'll be a slanting ramp of potential vorticity, some of which may be susceptible to erosion closer to the boundary, some of it might not be, and that can help to aggregate, perhaps.
I had the pleasure of being at a workshop with Brian Hoskins. I still don't understand PV, but would that show up across 1 degree?
Yeah,
Could you
I
see
think
that
so.
across
I
one
would
degree?
think so. Because the heating is so different in the cloudy and clear regions. It's elevation. And you might get disks of PV that are substantially different elevations.
I don't know. One thing which was super cool about this experiment, like very modern approach, is that all the data is online and available through a single point. Like, you can get a Python intake catalog that'll point you to every measurement made during Eureka. And I don't know a single person who's looking at it in that perspective.
Yeah.
So that it could be super interesting.
One more quick question. Go down here.
So this picture on the diagram that like you showed to me earlier, but like you're showing again in the top left here with the two, that really is kind of like it's stuck in my head. You know, it's like being like a fly buzzing in my ear right now, and I really want to get to the answer of this because I think this is actually interesting and important because I want to know, you know, because like one of the things I mentioned to you when I went to a meeting is that in observations you do see kind of this compensation between like the vertical transport of static energy by convection and the radiative heating, and they tend to act and cancel each other out. Like shallow convection tends to moisten, but the radiative cooling dries, and then it kind of reverses in cloudy regions. And I'm wondering if like this seems to be speaking about a potential solution of this in terms of the radiative cooling being on the relative humidity gradients. Related to this question is like, have you like done integrated vertically the right-hand side column to see if the radiative flux actually how it looks like with compared to the relative humidity? Because
Sorry, you're asking, has anybody looked at the
vertical integral of the right plot, you know, to get the radiative fluxes to see if they look like the, you know, because it sounds like it should look like the relative humidity based on the discussion you just gave, right?
Oh, I don't think we did that on Alea's paper, but that's, I mean, that data set you could access online in 10 seconds and you could completely do that.
Do you have the link? 'Cause
I'd be happy to show you how to do that.
Oh, yeah, that'd be great, because like, if I imagine the convective mass fluxes of the shallow cloud being proportional to the relative humidity, then my thought right now is that the radiative fluxes and the convective fluxes might actually be in phase and actually cancel one another out to a large degree in the MSC budget. But we can talk about that offline.
Yeah, so let me just point out that the Barbados Cloud Observatory has all kinds of interesting measurements, including ones that might be possible to, you might be able to infer cloud convective, shallow cloud convective fluxes.
Oh, okay,
From
that's
that
cool.
research, yeah.
That's cool.
There was one question online if you have time.
Maybe in the interest of time, we should
Okay.
call it quits and leave
If
questions
they,
for later.
if they have a question, they're welcome to email me.
It's Larissa.
Oh, I see. Oh, I had hoped she would be here. Okay. but-
She's watching online.
Cool. Yeah, no, she can email me. That'd be great. Or I'll stop by.
Let's thank Robert again.
Thank you.